Hello from my side. My name is Heiko Herden, and I am the chair of the OPC UA for Machinery Working Group. And in this presentation, I want to show you how OPC UA for Machinery is the base specification for discrete production. I'm working at the VDMA, and so I would like to start with showing what the VDMA is and what the VDMA does. So the VDMA is the Mechanical Engineering Industry Association of Germany and Europe, and it represents over 3,600 member companies in the engineering industry. It's structured in 35 different trade associations, each representing a different domain. And the main work of VDMA is to support all its member companies. And so that's also, of course, my work to support the member companies by helping to standardize information models for the production. So if I say already standardizing information models, why do we need it? So at the moment, there's many buzzwords flying around, and all is around Industry 4.0 and smart production. There's buzzwords like Internet of Things, condition monitoring. A very big buzzword at the moment is artificial intelligence. Then you also want to do predictive maintenance in these times where you exchange some parts before they actually break down so that your production can keep running. You want to do traceability, that you want to know where is my part coming from, which materials went into that part, maybe also what's the CO2 footprint of that. You want to save energy costs by doing a load management. You want to do remote services. And of course, there's also the big buzzword plug and work. You buy a new asset, you plug it in, and it works. And to fulfill all these buzzwords, you need to have one thing in common. You need to be able to access the data, the information coming from the shop floor. That means easily accessible and standardized shop floor information is the key. And this is the economic driver to do standardization in the field of interoperability. But there's not only this economic driver, there's also a second driver, the driver of regulation. I brought here one example, which is the EU Data Act, a new requirement by the European law. There's also QR codes on the side which you can follow to get an explanatory video of the EU Data Act. But in general, it says that data must be accessible for users in certain ways. It needs to be accessible easily, securely, comprehensive, and structured. And this is valid for all the data generated during the operation of a connected product which was put into the market in the EU. And so you can see here, on the one hand, we need the data for all these buzzwords that I've already shown that you want to do from your side, but you also need to have this easily, securely, comprehensive, and structured data available to fulfill the regulations. How do we do this? By using standards, by creating a manufacturer-neutral interoperability. It's a big word, interoperability, but you already know it from your consumer environment. So for example, if you buy a phone which supports the Bluetooth standard and you buy a car which supports the Bluetooth standard, then you usually can connect those two devices and it will work. That's plug and work. And that's what we also want to achieve in the industrial environment, to be able to connect different assets with each other more easily and also to use the data these assets produce. But the problem is that the industrial environment is way more complex than the consumer environment. Here's an example about the complexity of the machine building industry. So I brought pictures of different kind of machines. And you can see here, for example, a geometrical measurement system, a machine vision system, a machine tool, a weighing scale, a robot, or a winding machine. And as you can imagine, all these machines not only look different and work different, but also their data that is produced and transferred looks very different. So all these machines at the moment have very different interfaces. And without standardization, someone who is not familiar with the machine will have big troubles to understand the data and to work with the data. But we want to create interoperability. So how can this be solved? And the answer to that question is by standardizing. By standardizing a clear definition of the structure and the content of this information. And for this, we use OPC UA in combination with companion specifications. The upside of the OPC UA technology is that it comes with a lot of benefits that we need to achieve our goal of interoperability. So we can do information modeling, but it also has discovery services as part of OPC UA. It has security built in by design, and it has different transport mechanisms. So we can have a one-to-one connection as a client server or a one-to-N connection as publish subscribe. But for us, the important part is really the information block. We want to do information modeling. We want to say, what is the structure and the content of our data? And for that, we also use the OPC UA meta model and the built-in information models like OPC UA for devices that are already existing under the hand of the OPC Foundation. On top of that, we define OPC UA companion specifications. For the field of mechanical engineering, the VDMA always takes part in that, also to do harmonization. And on top of that, I can still do some vendor-specific extensions of the information models. This can be done, for example, if I have some data points that I don't want to standardize with my competition because I'm the only one who delivers them anyway. And so this is the overall picture of how it could all work. So for us, the important part are the OPC UA companion specifications. These companion specifications are already published in a great amount. So as you can see here on this slide, we have more than 120 publications already. So these specifications that are listed are already out in the first and the second and the third version. Often some content is added in future versions. And here you can see in bold letters that the OPC UA for machinery specification, which this is mainly about now, is already out with several parts. And also we have a lot of domain-specific specifications, like for robotics or metal forming or mining or wire harness manufacturing or flat glass cutting, weighing technology. There's really a lot. You can see if you can find your domain in that list. And of course, you could also download that specification then. It's available free of charge. And even more specifications are upcoming, as you can see on the right side, like for battery production, for cleaning machines, for electrolyzers, and so on. How does this then work together with a harmonized specification? I brought here an example which shows that this is overall a modular system. So I have the OPC UA for machinery specification, which is in harmonization as the base. So in this, we solve things that is the same for all different assets, like the serial number, a manufacturing name, um, overall running time of the machine, and machine state. All these things can be solved one time for all to be really interoperable. And if we now look into a single interface, like for example, the interface of a laser machine, we will see that it combines OPC UA for machinery for the basic information plus OPC UA for machine tools, because a laser is just a more specific machine tool, so to speak. But then there are some very laser specific contents in the interface, and these come from the laser specification. A bit more simple example would be a woodworking machine. There I just combine the base specification OPC UA for machinery with OPC UA for woodworking. For the user, that's pretty easy because the user knows, okay, I'm interested in woodworking machines. I'm a manufacturer of a woodworking machine or a customer of woodworking machines. Then I just look into the companion specification for woodworking, and there I will see that machinery is referenced. So as user, I only need to look at the endpoint. So now I talked a lot about why we need OPC UA for machinery and how it really standardizes all the data that is common for all. And next, I would like to give you an idea how could such a data model really look like. So you have your machine, and first of all, you have the block of identification, an object containing all relevant identification information. And this could be things like a serial number, a manufacturer, a model, a location, or initial operation date, or much more parameters. Um, I just picked out some examples, and overall, this is only a simplified and non-exhaustive representation of the machinery model, but it's meant to give you an idea about what is OPC UA for machinery about. And these parameters mostly come out of the devices specification. We made two mandatory, the serial number and the manufacturer, to ensure an unambiguous identification, and all the other parameters are optional and can be used if required or not. So this is pretty clear. Every machine needs an identification. But we have more. We also have a monitoring object. In that monitoring object, we have all the information aggregated that is monitoring information. And we divide it into 4 different categories, into status, health, process, and consumption. And within these categories, there are definitions as well. So within the status, we have 2 state machines. We have the machinery item state, which defines the state of the machine. Is it currently not available, which would mean we can't reach it? Is it out of service, which would mean it's not operational? Not executing means it could be it's operational, but it's not working, or executing, which means it's available, operational, and working. And there's a second state machine, the machinery operation mode, which describes what kind of operation is being done right now. Is it a maintenance operation, a setup operation, or a processing operation? And as you can see, these are the definitions within OPC UA for machinery that you could find in the end in that status folder and the monitoring folder. Of course, there's more definitions, for example, for consumption. There you could have information about an electricity consumption, compressed air consumption, and then these again contain different parameters, like for example, for the electricity, current, voltage, and power in different ways, or for the compressed air, measurement parameters like pressure, temperature, volume, and flow rate. And of course, there can be many more possible media information, for example, for steam, hydraulic oil, water, fuel, coal. There's lots of possibilities. All of those you could find in that consumption object. And this was already standardized in OPC 34100 energy consumption management. So as you can see, even in that harmonization approach of OPC UA for machinery, we are using a more generic harmonization, which was done in that energy consumption management specification, which looked at all kinds of different energy standards and made a harmonization of that. Then furthermore, we have the machinery equipment. This is also a folder aggregating all the information about temporary used equipment like tools, and also coming with the definition of different parameters for tools like a type ID, a device class, an asset ID, a location, and some more. Then on top of that, we have the notifications folder. In that, we have with that, we have an entry point for all notifications, which can contain events or alarms. And now this might be the biggest block in OPC UA for machinery. We have also the job management. The job management is based on ISA 95 job control. So once again, we used something that's already existing. We didn't start on a white paper or reinvented the wheel. We are always looking what is already defined, then we use it, and if necessary, we enhance it. And in this example, we added a lot of parameters which are needed for the mechanical engineering industry, but overall we are using the concept from ISA 95 for job management. And job management means that we have a job order, which comes from a higher level system, sent that to a machine with all the data that comes with it. Of course, a job name, but also which materials required, when is it supposed to start, how many parts should be produced, and so on and so on. In between, I get an update about the job, so I can see how many is done already, what's the current status of the job. And in the end, I get a job result, of course, where I will also get the job name back, but also will know which material was produced, what was the actual start time, what's the bill of material. I get some performance information of the job, so which forces or temperatures were used for creating that product, which I can also use to assure quality afterwards, of course. And then last but not least, at least for this example, like I said, it's a simplified example, but every machine, of course, has components as part of the machines. And these components, again, follow the same structure as a machine. So in this components folder, I have all the components and their information. And then, for example, here I have two components, and each component, again, has this standardized, harmonized structure with an identification object, a monitoring object, an equipment object, and so on, whatever I need. It's a lot of optional objects. And here I can have basically unlimited components as part of my machine, and I can even have components as part of my component. And so I think you can really see OPC UA for machinery as this generic approach, which is applicable for all the domain-specific companion specifications. And the benefit is quite big because think of a production line. I brought here an example where we have different modules, a sawing module, a painting module, a packing module, and a checking module. And now with OPC UA for machinery, I get the information from them all in the same standardized way. I see how they are named. I see the current status of these machines. I can see the current energy consumption of these modules all in the same way. And this is, of course, great for factory operators to fulfill a lot of different use cases. And so as an outlook, I can say OPC UA companion specifications, especially OPC UA for machinery, really are enablers for a lot of these buzzwords I mentioned in the start. You can run an AI, artificial intelligence, to work with the data that you finally get and understand. You can fulfill the EU Data Act. You can fill a digital product passport. It can be used for use cases within data spaces or manufacturing X. You can use it to fill up your product carbon footprint, to have a digital twin, or to do KPIs like an overall equipment efficiency. So there's a lot of benefits in using OPC UA together with companion specifications and especially the harmonized companion specification OPC UA for machinery. And so I come to my summary. You saw data is the key for Industry 4.0 use cases. The usage of OPC UA and companion specifications provides a secure, easily accessible, and self-evident data. And it's a good starting point to use the harmonized OPC UA for machinery specification. So if you didn't use any companion specification yet, then my advice is to take a look into OPC 40001 Part 1, which is the basic building blocks of OPC UA for machinery, which contains most of the things that you have seen in that tree structure that I have just shown you. And all the standards are available free of charge. We put a lot of work into these standards, a lot of companies, a lot of working hours, and we want the community to benefit from it, so they are free of charge available on the page of the VDMA, but also on the page of the OPC Foundation. So thank you very much for listening to this presentation. And if you have any questions, then don't hesitate to ask. Thank you.